different ranks or different types. Okay, so there is a tensor. In general, we define the tensor of type Mn. Okay, and then we are in the process of defining what is known as the contraction. Okay, so I define the concept of contraction here. Okay, so this is the contraction process. Okay, so the contraction is basically a process which gives me, if you give me tensor of rank Mn, okay, then I will get a tensor of rank m minus 1 n minus 1. Okay, okay, so this is, and how we define, okay, how we define that uh, map. Okay, so we consider suppose we consider tensor of rank 2 1. Okay, the tensor of rank 2 1 is supposed to act on one dual basis and two normal usual basis. Okay, so this is basis 1, basis 2, and then there is a dual base. Okay, so tensor of rank 2 1 is supposed to act on this object. Okay, so that we get a number. Okay, but suppose if I keep this slot, for example. Okay, so suppose if I keep this slot vacant, okay, that is I represent it by dot, and what I will do, I will consider a vector and and vector with one index and the dual vector basis with same index, okay, and I will sum over j. Okay, what I will get is a tensor of lower rank. Okay, so suppose if I keep this slot open, okay, that means I am allowed to act on some vector. Okay, I am allowed to act on some vector here. I should put some sorry, so I think I'm making, so this is 2 1. Okay, so vector of rank 2 1 should is supposed to act on uh, so I think this is okay. So let us start from new thing. Okay, so suppose you consider a tensor of rank say 2 1. Okay, I consider tensor of rank 2 1. Okay, so let t be a tensor of rank 2 1. So on which object it's we allowed to act? We are allowed to act on, so suppose if it is 2 0, then we need two dual bases. Okay, so dual bases are denoted by upper i's, and usual bases are denoted by lower index. Okay, so 2 1, so I should act this t on ei, ej, and it is 2 comma 1, so I need another dual basis ek. Okay, so these are, sorry, these are dual basis and this is usual basis. Okay, so t is, when t act on this, okay, I will get this, I will get a number in on real line. Okay, okay, now suppose if I keep one of this slot, either this or this, vacant. Okay, I will denote that vacant slot by dot. Okay, and I will fill it with ej and ek. Okay, now this object, okay, this object is a vector, correct? Agree? Because these slots are occupied. Okay, so we are not allowed to act anymore on these slots. Okay, we only allowed to act this object, this entire object, on a dual basis. When I act this object on dual basis, I will get a number. That means this entire quantity is a vector, because vector, when it act on dual vector, I will get a number. Correct? Okay. Now Instead of writing ek here, suppose if I consider t is dot ej ej, and I will sum over j. Okay, right? Is this is known as the contraction of t. Okay, so your original t is a tensor of rank 2 1. So I consider a contraction of t, a contraction, because there are other contractions also. This is one contraction where the first slot is kept vacant and second slot is occupied, third slot is occupied. Is it clear? Okay. Now let us see what happens in terms of components. Okay. Tensor of rank 2 1 can be written as t I j k. Okay, and if I express this in terms of basis, then it will be ei direct product with ej direct product with ek. Okay, these are the bases. So I express this tensor t in terms of direct product basis, ei cross ej cross ek. So these are usual basis and this is dual basis. Remember, here I am acting t on this, so these are dual basis and this is usual basis. Okay, here I am expressing t in terms of as a linear combination of direct product basis. Okay, fine. Okay, now let us add this t on this object. Okay, but I have used ijk, so I should use some other indices here. Okay, so let us act on t acting on el. Sorry, I have to keep this slot vacant, so let me keep this slot vacant. Okay, I will act on el and I will act on e say m here. Okay, so what object I am going to get? T I j k. Okay, e I. So here there is a summation over I, j and k, that is assumed. Okay, e I direct product with ej direct product with e upper k. Okay, and this entire object is acting on this dot, that means there is nothing here. Okay, and then there is el and there is em. Okay, so dot means this will remain as it is. ej will act on this el, ek will act on this em. So I am going to get tij k ei. Okay, because ei is acting on nothing. Okay, and then ej el, I will get delta l j. Okay, and ek em, I will get delta, by definition of dual basis, delta k m. Okay, but this is nothing but, so there is a summation over I j k. Okay, so because of this chronicle deltas, I will get t I j will be replaced by l. Okay, k will be replaced by m. Okay, and ei. Agree? Fine. Okay, so this is the action of t on this. Okay, there is a summation, only one summation, there is summation over I. This indicates that this object is a vector. Agree? Because any vector can be expressed as a linear combination of these. Okay, so these are fixed indices now. Okay, and this is a running index I. Okay, clear? So now suppose if I, instead of m, suppose if I consider, suppose now I will add t on el so I replaced m by l and I will sum over l. What I am going to get? So used your previous relation, So TILMEI, summation over I. TILMEI, summation over I, and then I have to replace M by L. So I will replace M here by L, and I will sum over air also. Okay, so this quantity, okay, is nothing but, so now I will not write summation here. Okay, so I will just write TILLEI. Okay, so what does it mean? The component of this quantity, okay, component of this is Ti. You can use any other index, say K. So this is the component of this. Okay, so there is only one free index. This is summed over. Okay, so this is a contraction of Tijk. So instead of writing T, I can talk about contraction of. So when I say tensor, I sometimes refer to tensor in component form. Okay. So why I say a contraction? Because I could have defined another contraction. Suppose if I define TEL dot EM or EL, I will write directly now, summation or L. This will define me another contraction, right? What kind of contraction is this? Can you tell me directly? It will be TKIK. Okay, and there is a summation or K. So this K is repeated, so K is summed over. So in general, this is not equal to this. This contraction is not equal to this contraction. Clear? So you can see by changing the position of the slot, empty slot, I get different contraction. But now I cannot put this slot here because I require at least one covariant index, right? Okay, I cannot have contraction for this. I cannot have, so this is one contraction, this is another contraction. Okay, so I cannot, suppose if Ij and there is nothing here. Okay, so this is the tensor of type 20. I cannot define contraction on this. So to have a contraction, we require at least one covariant and at least one contravariant index. Those two index we can contract. Okay, so in terms of components, so you have this tensor of rank 2 1. So first you consider tensor of rank 2 1. So instead of doing all this process, you can understand this process in the following way. Okay, you first write the tensor in component form Tijk. Okay, so to obtain a contraction of this tensor, okay, let us consider any one of these, any one of either I or J, and replace it by the same index K and sum over K. Okay, so one contraction is T K J K. So there is a summation over K. Another contraction is T I K K. Okay, so these two contractions are not same in general. If it happens that this tensor is symmetric in upper two indices, that means this Tijk is equal to Tjik, then these two are same. Okay, right? So you can see you need this index. Similarly, Suppose you consider a tensor of rank 1, 2. Okay, then first what we need to do, you consider its component version T, I, J, K. Okay, and now I want to define a contraction. So I, K, that is one contraction, and another contraction will be T, I, K, I, right? Okay, so this is very simple. This is known as the contracting a tensor. So you can generalize this. Okay, so suppose if I give you a tensor, now I will write only directly in component form. Suppose if I consider a tensor of rank say 3, 2, I, J, K, L. Okay, and I want to contract it. Okay, what will be a contraction? So now you have to ask me which index you want to contract. Okay, so it will be given to you. So contract first lower index and third upper index. Okay, so it will be I, J, K, K, M. Okay, so this will be one contraction. This will be another contraction. I, J, K, J, K. This will be another contraction. Third will be, you now shift this index here. Okay, so T, I, J, K and J, M. This will be another contraction. Fourth one will be T, I, J, K, okay, and L, J. This will be another contraction, and so on. You can list many contractions here. Is it clear? Okay. So at in each example, you can see you will get if you start from tensor of rank Mn, you will get tensor of rank M minus 1, N minus 1. Clear? Hmm? So you cannot define contraction on a vector. So vector is defined by the component Vi. So you cannot, there is nothing you can contract here. Similarly, you cannot have a contraction on covector. Okay. Good. So this is nothing but the contraction, process of contraction. So it will be useful later on. Okay. So this is just a process to obtain a lower rank tensor from a given tensor. From a given tensor, you obtain lower rank tensor. Is it clear? Any question regarding this? Is it clear?
Sir?
Uh,
Sir, so physically speaking, what does this contraction signify? Like,
we,
if I
will
am
we'll come
operating
to
my...
that. We'll come to
Okay,
that. We'll come to that.
okay,
Physics, I have not yet introduced, I have not yet started discussing physics of this, but we'll come to that.
okay.
Okay. Any other question? Okay. So now the next point is, so now we have we discussed vectors, dual vectors, tensors, okay, different types of tensors, and a process called contraction. Okay. Now let me introduce the concept which you know already, that is inner product space. Inner product on a vector space. Okay. So what is our inner product? Let V be a vector space Okay. So inner product is a linear operation, okay, which gives me, it takes two two vectors from this vector space and gives me a number. Okay, number means an element in the field over which I am defining this vector space. Okay, so it is a map from V to R. If our V is defined over real numbers, field of real number, then it is a map from V to R. In fact, it is a map from V cross V to R. So inner product is a map from V cross V to R, such that, okay, so inner product is denoted by symbol like this. Okay, so you put something here, something here. Okay, so this is a map from V cross V to R, such that V W for any two vectors V and W in capital V, inner product of V and W is equal to inner product of W and V. Okay, so this is the first, it's called symmetry property. Second one is this map is linear, that means V inner product with alpha W1 plus beta W2 is equal to alpha 1 V W1 plus alpha, so beta, why that is alpha 1, so there is no alpha, it's just alpha V inner product with W1 plus beta V inner product with W2. Okay, similarly, if I replace V by alpha V1 plus beta V2 inner product with W, the linearity holds. So it is linear in first slot as well as linear in second slot. So it is a bilinear operation. I'm not writing the second one. Okay, so it is a bilinear operation. Okay, it's called symmetric. Okay, and third one is for V not equal to zero vector. This zero is zero vector. Okay, there exists a vector W belongs to V such that, okay, V inner product with W is not equal to 0. Okay, so for any non-zero vector, there exists a vector, another vector W in V such that V inner product with W is non-zero. So it's called degenerate. Okay, so symmetry degenerate bilinear form is nothing but the inner product. Okay, so this inner product is a map from V cross V to R such that this satisfies. Okay, on top of this, suppose our V is Euclidean vector space. Here actually I consider Euclidean vector space, but in general I may not consider Euclidean vector space. Okay, suppose our V is Euclidean. Okay, then the following hold. Okay, V inner product with V, okay, is greater than or equal to 0. Okay, it is 0 if V is 0. Okay, so equality holds only when V equal to 0 vector. Okay, so this is for Euclidean vector space. For other type of spaces, for example, the space which we are going to use, Minkowski space, this does not hold. Okay, fine. These three are essential. This is the defining property of inner product space. So you must have gone through this, okay, in your MMP1 course. Okay. Now let us consider now, from now onwards, we will talk only about the inner product spaces. That means the vector spaces equipped with inner product. So what are the example of inner product spaces? So consider Rn or R3, for example. Okay, so this is inner product space. So let us consider two vectors v and w. Okay, these are the vectors in R3. So v is denoted by, say, v1, v2, v3. Okay, so let me, yeah, so maybe I should, just to avoid the confusion, I will write this as, say, three numbers a, b, c. Okay, and w is uh, d, e, f. Okay, then v inner product with w is a, d. Okay, so it is just a, b, c and d, e, f, your usual definition. Okay, row and column. Okay, fine. So in a compact way, suppose if I denote v by, say, v1, v2, v3, and w by w1, w2, w3, then v inner product with w is just summation over I, vi, wi. Okay, this is the inner product. Okay, suppose if I consider a space, say a four-dimensional space, with, it is not R4, but I will consider a four-dimensional space with the following inner product. Let v and w be vectors in this four-dimensional vector space. Okay, so v is v1, v2, v3, v4. W is w1, w2, w3, w4. I define the inner product as v1, w1, okay, minus v2, w2 plus v3, w3 plus v4, w4. Okay, so this is not the example of Euclidean vector space. This in fact is Minkowski space. Okay, right. So this inner product, okay, this definition of inner product satisfy all these axioms 1 to 3. Okay, but not this. You can understand why. Okay, because of this minus sign, I can have this equal to 0 by adjusting this quantity with this. Okay, so I can have 0 here on right hand side without putting v equal to 0. Okay, so this is the example of your usual Euclidean vector space, and this is your Minkowski space. Okay, I will come to this. We'll discuss this in detail. Okay. So what is the point? The point is, once you have a vector space with inner product defined, I can talk about a dual vector corresponding to given vector. Okay? There is a one-to-one mapping between a vector and its dual vector. In general, we can have, for a given vector space, we have a dual vector space, but the mapping between vector and dual vector is not one to one. Okay, we can, at least we cannot prove that. In other words, v and v star or v tilde, okay, v and v star, so v star is a dual space to v. These two vector space may or may not be isomorphic if we don't define inner product. If I have inner product defined, then V and V star are isomorphic. Okay, that means given a vector in V, I can uniquely construct a vector in dual space. There is no difference between vector and dual vector space now. Once I have the inner product defined, how it works? It works in a following way. Okay? So you have a vector space V with inner product defined, okay, and let me consider V star be its dual space. Okay, let V be small v be element of capital V. Okay, I will also define a basis for uh, this vector space V. Hmm? I will also define a basis for this vector space V. Okay, so corresponding to this vector V, okay, I will define a dual vector V tilde in following way. Okay, see the dual vector by definition, it is supposed to act on a vector to get a number. It is a linear function. Okay, so it will act on a vector to get and I will get a real number. So this is the vector, this is the dual vector. It will act on this empty slot. Okay, this action I will define in a following way. This action, whatever this number, whatever this object may be, okay, some vector is there. I will just simply denote it by dot. Hmm? Okay, so this action is defined to be inner product of V with that dot, whatever that vector may be. Okay, so you assign to this vector a dual vector. Okay, by through this inner product, because inner product is also real number. Inner product of two vector is a real number, and action of dual vector on vector is also a real number. When I have this inner product defined, I am just saying that these two real numbers are same. Hmm? Okay, so given a vector V, I am assigning to it a dual vector in this way. Okay, clear? So for example, suppose instead of dot, suppose if I put, say, if I act this V tilde on, say, basis E1, okay, what I'm going to get? Okay, this action is defined as inner product of V with E1. Okay, fine. So inner product of V with E1 is definitely a real number. Okay, that real number is assigned with action of V tilde on E1, and this assignment is one to one and on to. Okay, one can show that this assignment is one to one and on to. Hence, this mapping is isomorphic. So mapping between V and V star is isomorphic. Hmm? Okay, so you can define, you assign in a natural way a dual vector to given vector. That's why we require inner product. That's why the inner product spaces are important. Okay, there is a natural assignment between vectors and dual vectors. If you don't have inner product, then we will have dual spaces, vector spaces and its dual space, but there is no natural correspondence between these two, between V and V star. Given the inner product space, we have the natural correspond the natural association between vectors and dual vectors. Hmm? Okay, fine. But you must remember that This correspondence, okay, through this correspondence, we may or may not get, suppose, okay, we may or may not get the equivalence between the bases. What do I mean by that? We have already considered a dual basis for V star, right? How this dual basis is defined? Given the basis EI for vector space V, then dual basis corresponding to this is defined through this EI. How it is defined? Action of EI on this vector EJ is chronicle delta IJ. This is how we define. But now if I use this map, okay, now suppose if I consider say E1, okay, and corresponding to E1, suppose somebody say that this is my dual basis, okay, E1, E1 tilde, okay. What I am saying is that this E1 tilde may not be same as your E1, this E1, okay, which which is defined through this relation. So you must be very careful. See, there are, is this point clear? Corresponding to a dual space V star, you have a basis, dual basis. How this basis is defined? This basis is defined through this. Okay, this is the dual basis. Okay, for a given basis for V, I have a dual basis for V star. Okay? And this dual basis is defined through this relation. Now we have defined a correspondence between vector and dual vector. Using this correspondence, we may or may not get appropriate dual basis vector corresponding to E1. May or may not. Hmm? Let us see how. Okay. So let us consider a dual vector U tilde. Okay, and let us ask the question. Okay, so this is the dual vector corresponding to a vector V. Hmm? And let us ask the question: what are the components of V tilde? What are the components of V tilde? So I have a vector space V and I have basis defined EI. Okay, and let V star be a dual space and let E EI be the dual basis. Okay, there is no tilde here. Hmm? Okay, now the question is, what are the components of V tilde? Okay, which is a dual vector corresponding to V. Okay, fine. So how, let us see how we can get the component of V tilde. Okay, by definition, V tilde acting on say EI, what will be the result? This will be some number, right? This will be some number. Let us denote that number by Vi. Is some real number Vi. Okay, now I will use this correspondence. Okay, Vi is equal to V tilde acting on EI. Okay, but what is this V tilde? See how we define this correspondence. V tilde acting on EI is same as V inner product with EI, because V tilde is a dual vector corresponding to V. Clear? Okay. But V is any vector in this vector space that I can write as linear combination of this basis. Okay. So let me write another. Let me take another index J. So it will be Vj Ej. Remember that we choose to denote component of vector by superscript. Okay, and inner product with EI. Okay, but this inner product is a linear, so this Vj will come out. There is summation over J Vj, inner product of Ej with Ei. Okay. Now there is no reason for me to assume that Ej inner product to Ei is delta Ej. Okay. Is it clear? If basis Ej or basis set Ei is orthonormal basis, then Ej by definition Ej inner product with Ei is delta Ej. Correct? This is same as Ei inner product with Ej because of the symmetry property. Hmm? So if we are using orthonormal basis, then Vi is equal to, I will directly write this, summation over j Vj delta Ij. That is nothing but Vi. So if I use orthonormal basis, then component of vector V, component of V in basis Ei is same as component of its dual vector in basis, in which basis? Dual vector is defined in dual space. Dual space has this basis in basis. Okay, but this hold only when this happens. Because of this, is it clear? In general, I Vi is not equal to V lower I is not equal to V upper I. That's why we distinguish between components of vector and dual vector by upper and lower index. In general, they are not same. If your basis is orthonormal, then they are same. And this is usual case. Okay. We are familiar with this, okay, from the beginning. Okay, your Cartesian coordinate system, you choose orthonormal basis. Once you choose orthonormal basis, there is no distinction between vector and dual vector because their components are same. So there is no need of using upper index, lower index. Hmm? Okay, but if your basis is different, then the components of vector and its corresponding dual vector, they are different. Okay. You can do this, you can take this as an exercise. Okay, you consider a vector space V, you consider V to be R2. Let us consider basis vectors to be 1 0 0 1. Okay, and let us consider vector V to be say 1 2, vector 1 2. Okay, so exercise. Okay, so calculate the component of dual vector corresponding to 1 2. Okay, so just to familiarize with this, what will come in the calculation. Okay, so what are the components of V in this basis? Components of V in this basis is, you can write this as 1 times 1 0. plus 2 times 0 1, right? Okay, so the components of V are V1 equal to 1 and V2 equal to 2. These are the components. Okay, upper index, and basis, this basis is E1 and this is E2. Okay, now what you have to do, you have to find dual basis. What is the dual basis? 2 1 0 and 0 1. What is the dual basis to this? That you have to find. That I will denote by B star. Okay, so this is E1 and E2. These are the dual bases. Okay, now you have to write this same, you take this vectors 1 2, okay, and write this same vector in this dual basis and collect the components. Okay, that is one thing. Then you consider action of this 1 2. Okay, you use this map, you use this way, okay, and find the components. And show that the components of vector in this basis, that means these are same as component of corresponding dual vector in this basis. Okay, so this is the example showing if the bases are orthonormal, then the components of vector and the corresponding dual vectors are same. Now you consider, this is exercise 1, then exercise 2. Now you consider same R2, okay, and choose bases 1 1 and 1 0. Certainly this basis is not orthonormal with respect to your usual inner product for R2. Okay, you can again consider same vector. Okay, you find the components, and then you consider the corresponding dual vectors and use the previous result, this result, and find the component of dual vector. And show that this time the components are different, completely different. Okay, so it means that for a given inner product spaces, okay, the first point is that there is a natural correspondence between vector and dual vector. Given a vector, you know definitely what are the components of dual vectors. Okay, for that you need to use this. Okay, so given a vector V, okay, if the vector is given, that means these components are given, and it is the inner product space. That means you know this action, you know how to calculate this Ej inner product with Ei. That means the right hand side is known, but right hand side is equal to Vi, so you know the component of dual vectors. Okay, uniquely. Second point is that these components are in general not in agreement with the component of vector. Okay, fine. It is, they will agree if and only if the basis is orthonormal. Basis you choose to express V is orthonormal. That means these EIs are orthonormal. Okay, fine. This quantity has a special name. It's called the metric tensor. Okay, we'll see how. Okay, at least you can see that indices wise it is Ij, all are lower, all are subscripts. Okay, and there are two subscripts, so it is a 0 2 type tensor. Okay, So this is basically your metric tensor. So now we'll define what is known as the metric tensor. Okay. Any question so far? Hmm? Any doubt? Any question? Is it clear? Everything? No question? Should I proceed?
Yes, sir.
Okay, fine. So now we'll define the metric tensor. Okay, metric tensor is type 02 tensor. Okay. Okay. So metric tensor is type 02 tensor, and we usually denote it by eta, such that eta type 02, that means it should act on, to get a number out of eta, we must act this eta on two vectors. So VW. Okay, so these are two vectors. So eta acting on VW is same as eta acting on WV. Okay, so it is basically satisfies same property as your inner product. So instead of saying inner product, I am saying it is a metric tensor. Okay, it is by definition this is a tensor, so it is a bilinear. Okay, so eta V alpha W1 plus beta W2 is equal to alpha eta VW1 plus beta eta VW2. Okay, so instead of saying that inner product between V and W, I say that eta acting on V and W gives me a number. Okay. In practice, to calculate action of eta on VW, we just use the inner product. Okay. And third one is eta acting on VW. Okay, is not equal to 0 for V not equal to 0. Okay, so I should say that for non-zero vector there exists a vector W, okay, such that this happens. Okay, so this is the defining properties of metric tensor. Okay, clear? Okay. Now, since it is a 0 to tensor, okay, recall that any 0 to tensor can be expressed as a linear combination of direct basis product, direct product basis. Okay. So eta ij, okay, eta equal to eta ij e I sorry, should, yeah, it is 0 to, so it will be ei direct to ej. Okay, and these are the components of metric tensor. By definition, this is symmetric. Eta acting on WV equal to eta acting on VW is same as eta acting on WV for all W and V, okay, belong to V. Okay, clear? So this implies that this first property implies that eta ij equal to eta ji. Clear? Okay, so this is your metric tensor. The action of how you determine this eta ij, how you will determine this eta ij, you simply act this eta on basis ei, where you will act this eta. Eta is supposed to act on two vectors. Let us choose these two vectors to be basis vector ei and ej. Okay, then this ei ej, first I will use the definition of expansion of eta in terms of direct basis product, direct product basis. So it will be eta I, so I have used ij, so I should use say lm, eta lm, el em, and this will act on two bases. Okay, so this will be equal to eta lm. There is a summation or l and m assumed. Okay, el acting on ei and el acting on ei and em acting on ej. So this will give me delta li and delta mj respectively. Okay, so this will be equal to eta ij. So there is a summation or lm. Okay, so eta acting on ei ej is eta ij. So these are the components. So this is precisely these components. Okay, clear? So basically this, to calculate the action of metric on these two vectors, you need only the definition of inner product. Once you know the inner product, you are actually giving me the action of metric on two basis vectors. Okay, for example, suppose you consider R3, okay, with usual inner product. Okay, so I will choose the Cartesian basis here. Okay, so with usual inner product, I mean ei inner product with ej is delta ej. Okay, then what should be the metric? Metric ei, eta acting on ei ej is same as your inner product. Is ei ej, that is delta ej. Okay, so the component of eta in this basis will be eta ej, that is same as delta ej. So in this basis, your eta matrix will look like 1 0 0 0 1 0 0 0 1. Is it clear? Okay. But you can use different bases. For example, you can use polar basis. Okay, and you can calculate the metric. Clear? Okay. Now, given the metric, okay, I have already mentioned that given the inner product space, if I know the component of a vector, then you know the component of dual vectors. Okay, so let us consider V to be a vector in V, capital V. Okay, then the component of dual vector corresponding to V, that is denoted by V subscript I is equal to summation over j. Okay, remember our earlier calculation, vj ei inner product with ej. Okay, but this is same as summation over j vj eta ei ej. Okay, fine, but this is equal to summation over j vj eta ij. Okay, eta acting on ei ej is just eta ij. Okay, so given the component of vector, that means these quantities are given. By doing this computation, you know ith component of dual vector. Okay, so you can see now that in usual R3 with Cartesian basis, okay, eta is diagonal matrix with diagonal entries 1. Hence, there is no difference between Vi and this V lower I and V upper I. They are always equal. V lower I and V upper I. They are always equal for Euclidean space with Cartesian basis. Cartesian and orthonormal basis. Okay, is it clear? So in a sense, okay, so I will not write summation here. I will just write here eta ij vj. Okay, summation over j is assumed. In a sense, I am lowering the index of this v. This, what is happening? You see, this upper j is lowered through the action of eta, and I am getting v lower I. So it is called lowering the indices, lowering the index of vector, and I will get a dual vector. Okay, I have lowered the index of v to get a dual vector, or the component of dual vector. Okay, so upper index is lowered now through this action. Is it clear? Okay, fine. You can do the same thing for any tensor now, right? You can do the similar thing for any tensor. Suppose you consider t. Suppose you consider a contravariant tensor of rank 2, Tic. Okay, you can lower this index. How you will lower? Suppose I want to lower this index. What object you will get? By lowering this index j, I will get an object Tij. How you can lower this? Okay, how you can lower this index? Hmm?
Contraction.
Pardon?
Contraction.
No, it is a lowering. It's not contraction. Contraction you will get, you will lower the rank. I'm not lowering the rank. Okay, I'm
By the action of matrix.
so how you will do that now? So for a vector, what we did, v upper index and v lower index. Okay, one eta is sufficient, right? And you see how these indices are placed. Eta ij is symmetric tensor. Okay, so eta ij is same as eta ji. So this indices doesn't matter. Okay, so indices which is summed over is the index appearing on the vector, and free index is the index which is appearing on dual vector as a component of dual vector. Okay, Clear? Now I'm saying that okay, so I have given you yeah, yeah. So now I have given you the tensor of rank 20, that is contravariant tensor of rank 2, and I want a mixed tensor of rank 1. Okay, so this can be done by using one metric. So eta. So first I will write that tensor Tij. Okay, and I I my aim is to get this tensor. Okay, so upper index is I, lower index is j. Okay, so upper index is I. If I place j here, I will never get lower index as j as a lower index. Correct? Okay, so I need to place j here. Okay, eta j k, and then I need to put place k here and summation or k. Okay, so if I sum or k, then eta ik tik will give me eta ij. Okay, summation or k is implied. Clear? Similarly, you can, starting from this t, okay, say t ij, you get t lower I upper j. How I can achieve this? From this, you write first, you have to write first fixed index, so that is j is fixed, so j don't change its position. Okay, I should come down, that down index should come on metric, then k, k, and summation or k is implied, eta ik tkj. Okay, this is nothing but tij. Now you see these two are not same. Unless there is some other property, these two are not same. Okay, similarly, suppose if I give you a tensor, say of rank 1, say Tij. Okay, tensor of rank 1, and I want tensor of rank 20. So I'm going other way around now. Okay. Can I do that? From tensor of rank 1 to tensor of rank 20. Can I do that with existing knowledge?
Inverse of metric tensor is required.
So you need, now you can see, I using just eta, I go from contravariant to covariant. So I have taken contravariant tensor of rank 2, and I am getting low the mixed tensors, or even I can get the covariant tensor of rank 02. Okay, for example, okay, instead of discussing this, let me say that from this tensor I want this tensor. Can I achieve that? Yes, I can achieve. Okay, so you write ti, you write eta, so you write t first here. Okay, now both indices have come down. Okay, that means what? I need some completely different two labels, k and m, say. Okay, and I need two etas because there are two indices which I wanted to bring down. Okay, so eta I k, k is some, is getting summed over this k, and eta j m, this m is summing over this m is coupled with this m, and they are summed over. Okay, so eta ik, eta jm, tkm. Okay, this gives me tij. This I can do. I can do it for any tensor of any rank. Okay, any contravariant tensor of any rank. Okay, so I, j, k, l, m, I can bring this tensor to completely lower. Uh, I can bring this contravariant tensor to covariant tensor. Okay, I, J, K, L, M by doing these successive operations. Okay, but I cannot go from here to here unless I define inverse of this operation. Inverse of this operation. Inverse of what? Inverse of, let me go back. Yeah, yeah, inverse of this. Okay, remember V tilde is a map from vector to number. When I add dual vector on a vector, I will get a real number. Similarly, I can act a vector on dual vector and I will get a number. So it is a map from dual vector to real number. Okay, so I can think of vector as a map from dual vector to real number. I can think of dual vector as a map from vector to real number. Okay, clear? Okay, but now if I have the inner product space, it's very easy to do. That is the point. Okay, so this is what we are going to do now. Okay, any question till now?
Sir, how that two metric tensor come in the first equation?
Huh? Because I see, because I have to lower two indices now. Okay, agree? So you, what does it mean? So this, let me write it in a expanded form. Okay, so T is a tensor of rank say 20. Okay, how you write this? Tij Ei direct product with Ez. Agree? Okay. From this, I want some other another tensor, say T prime, which is a tensor of rank 1 1. How you write this tensor of rank 1 1? T prime Ij E I direct product with Z. Clear? Okay. Now you remember for vector what we did, corresponding to a vector. Okay, I assign to this vector a dual vector. How I assign this dual vector? Action of this dual vector on say ei dual usual basis is equated with, is defined to be inner product of v with ei. Okay, yes. So through this I get a component. So this is nothing but your vi. This is nothing but your v lower I. Okay, so here if I express v in as a linear combination of ei, so I will get vi here. So from vi to vi, so in place of v, okay, I have a tensor of rank 20. Okay, Tij. Okay, fine. So now you remember, you go back to our last class, previous classes. Okay, we have a tensor space, right? Collection of all tensor of type 20, they form a vector space. That we have seen. Okay, a dual space corresponding to that will be a space of all tensors of rank 0 2. Clear? In previous class we discussed long back. Space of all the tensors, space of all tensors of type 20. is a vector space. Clear? We call this as a tensor space. Okay. I can define dual space to that. That will be a space of all tensors of type 0, 2. Okay. Now, once we have that spaces, you use this same thing. Okay. You will have, see, why I'm getting your question was why I'm getting these two etas. Two etas will come corresponding, one corresponding to this and another corresponding to this. That's it. Is it clear or not?
Okay, sir.
Yes.
Yes, sir.
Understood or there is a doubt?
Yes, sir. Understood.
So you just you consider the action of t. You consider the action of t on say you suppose t prime is a dual tensor to this t. What you need to do? T prime must t is a tensor of rank 2 0. It must act on two dual vectors. T prime is a dual tensor to this t. That means it must act on two vectors, say EL and EM. Okay. Here, it's on one hand T prime, since it is a tensor of rank 0 2, I can write this as T prime LM or say TLM. TLM EL direct product with EM. Okay. Clear? Okay. And then I will act this object on EL, sorry, EIZ, say EI and EJ. This is one part. Another part is you consider corresponding to this T, you associate a dual tensor, say T prime, and we want the component of T prime in this basis. Okay, let us consider, let us say that Tij be the component of T prime. Okay, but since we don't have to write prime here, since the contravariant and covariant tensors are distinguished by lower and upper indices, so I don't have to write this prime here. Okay, this by definition is T prime acting on EI EJ. Okay, but T prime is this. Okay, clear? Okay, so this by our this definition, which definition? This definition. So a definition like this. Okay, V tilde acting on EI is defined to be inner product of V with EI. Now in place of V tilde, okay, you have T prime, and instead of EI you have EI comma EJ. Okay, now you apply successively this. You take this quantity, and you apply here and here successively. You require two etas for that. Okay, this is how this eta is coming. Is it clear? What I mean is the following.
Yes, sir.
ELM, EL, direct product, EM. Okay, this inner product with EJ. Okay, and EI, EJ. Okay, this is not a nice way of writing, but in a sense this is what is happening. So EL inner product EJ, EM inner product with EL inner product with EI, EM inner product EJ. Okay, This is how the two etas are coming. Hmm? Okay, so we have the way to go from contravariant tensors to covariant tensors. Hmm? Okay, but now, okay, now I can do the reverse thing. Okay, what I will do, I will consider a vector and I will action of this vector on any dual vector, okay, is supposed to give me a real number or a field over which the vector space is defined. Hmm? Okay, so remember this is vector and this dot now represents any dual vector. Okay, now if my space is inner product space, okay, then I define this action by V inner product with this dot. Sorry, V tilde inner product with this dot. So what I am doing, you try to understand, action of vector on any dual vector is equated with inner product of dual vector corresponding to V with another dual vector. Hmm? Okay, clear? But because the inner product is symmetric, this is same as V tilde. This is my association. Okay, for any dual vector, I associate a vector. Previously, what we are doing, for any vector, we are associating a dual vector. Now I will associate, for a given dual vector, I will associate a vector. Hmm? Okay, right? Now V acting on EJ. This is a basis dual vector, dual basis vector, jth basis vector in dual space. Okay, this by definition is inner product of dual vector with EJ. Okay, but any dual vector can be written as linear combination of component of dual vector that we normally denote it by subscript I, Vi, and then dual basis Ei, inner product with Ez. Okay, but this map is linear, so the inner product is linear, so it will be summation over I, Vi, Ei, inner product Ez. Okay, this by definition is the jth component of vector. So you have the same thing now. Vj is summation or I, V lower I, Ei, inner product with Ej, but this is inner product in dual space. Same inner product but in dual space. Hmm? Okay. Yeah. So now for a given dual vector, for a given components of dual vector, I have the component of a vector. Hmm? Okay, this quantity is denoted by eta inverse. See, this quantity is a number. Ei inner product with Ej, E upper I inner product with E upper J is a number. This number is denoted by action of eta inverse on Ei Ej. So eta inverse is a tensor of type 2, okay, such that all these previous properties are satisfied. That means eta inverse Ei Ej is same as eta inverse Ej Ei. Okay, it is linear, and eta inverse, if Ei is not is zero vector, then there exists a vector such that eta inverse v with w is non-zero. Okay, all those are satisfied. Okay, so eta inverse is the tensor of type 20. Okay, so with help of this, okay, you can write v upper j as summation over I v I eta. Now you see, this is a tensor of type 20. Okay, it implies that eta inverse can be written as eta inverse ij ei ej. Okay, here, so now you act on this. Okay, so you will get only eta inverse ij. Okay, but instead of writing eta inverse ij, I will just write eta ij. I don't have to write inverse because eta component of eta are eta ij and component of eta inverse are eta upper ij. So they are anyway distinguished. So I don't have to write inverse here. Okay, so eta ij. So vj equal to summation over I vi eta ij, eta upper ij. Once you have this, then again you can go from covariant tensors to contravariant tensors. Okay, so it is called, so previous operation was lowering the indices, now we are raising the indices. Okay, so I can use eta and its inverse to raise and lower the indices. Clear? And it's why we are calling this as the inverse. I could have said this is a completely different tensor. Okay, this is not any arbitrary tensor. Once you have this, once you define eta for a given vector space, okay, then corresponding eta is your 0 to tensor, then corresponding 2 0 tensor is already fixed. You don't have to do anything, it's already fixed. It is just inverse. This eta upper ij is the component of inverse of eta. Okay, it's not arbitrary tensor. Okay, one can show that it is in fact it is a component of inverse tensor of eta, in a sense that eta ij eta jk is equal to delta ik. You can show that. In fact, you can take this as an exercise. Okay, that show that this eta upper ij is indeed inverse of eta. So if you write eta as a matrix, okay, then this matrix is inverse of this matrix. That you can show. How you can show that? Can anyone tell me? What should be the starting point to show this? What should be the starting point? What should I do?
So defining the eta means the tensor as direct products, and then operating both
Direct
upper ij
product.
and
No, but I define eta as a, see, eta is defined as, eta is a 0 to tensor is defined as eta eta ei ej is equated with inner product of ei with ej. That's it. This is my definition, right? Okay, then what should I do? I want, now I am saying that eta inverse Okay, is eta inverse should act on dual basis, ei ej. This is defined to be ei inner product. So this is with ej. Okay, now what should I do? I need to show that this eta inverse, and if I take its ij and eta ij, eta ik, then this must be equal to delta ik. This I need to show. So what should be the starting point?
Action of eta on eta inverse.
Action of eta on eta inverse. What do you mean by action of eta on eta? Eta is allowed to act on two vectors, right? And eta inverse is allowed to act on two dual vectors. So what do you mean by action of eta on eta inverse? You want to think in terms of tensor or component? That you first fix and then answer. What should I do? What should be your starting point? Once you understand the starting point, then the proof will follow. There is nothing much to do. Suppose you consider the following. Suppose you consider the inner product of two vectors, say v and w. Start with this. This is your hint. Start with this. Okay. Clear? Think in terms of this inner product of two vectors. This is equal to, okay, what is this? This is inner product of vi ei summation over I and wj ej summation over j. So this is vi wj ei ej. Okay, clear? So this is nothing but vi wj eta ij by definition. Okay, through this definition, ei inner product with ej is eta ij. So this is your eta ij. Okay, now what you will do?
V tilde W tilde inner product.
So now, so this is nothing but what? This is equal to, you can think this as V tilde acting on W, right? Agree? But inner product is symmetric. So this, on other hand, this is equal to W on V tilde, W on V. This is nothing but W tilde on V. So these two are same. Correct? Okay. Fine. Okay. So once you use the definition of vectors and then you use definition of dual vectors. Okay. See, what I mean to say is this is also same as V acting on W tilde. But this is nothing but V tilde W tilde. Okay. Then you apply the same logic here. Then you will get eta inverse upper ij. And you argue that this should hold for all V and all W. It is not any particular V and W. It should happen for all V and all W. If it is the case, then eta inverse eta and this so-called eta inverse, they are actually inverse of each other. That you can show. Okay, so try to do this. Okay, I will not give any other hint. Okay, this is sufficient. Okay, try to do this. Show that eta and this symbolic eta inverse, they are actually inverses of each other. Okay, so this we have done for see, this is the general procedure. It applies to Euclidean space or even Minkowski space. Okay. Now, henceforth, we will restrict ourselves to Minkowski space. Okay, one can use it on Euclidean space as well, but we need tensors on Minkowski space, so we'll use the Minkowski space only. We will specify, we'll restrict to Minkowski space. Okay. So now, so vector in let V, so Minkowski space symbolically okay, let me define, right, 3 plus 1 dimensional Minkowski space. Okay, it consists of, okay, so any point in this space we label by 4 numbers x0, x1, x2, x3. Okay, these are the 4 numbers which are used to label any point in 3 plus 1 dimensional Minkowski space. Why I am writing plus 1 and not just 4 dimensional Minkowski space, it will be clear later on. Okay, so any point in Minkowski space is labeled by these 4 numbers. Let V be, so this is denoted by letter M4 or R3, 1. Either you use R3, 1 or you write M4, Minkowski space, 4 dimensional Minkowski space. So let V be any vector in M4. Okay, then V can be expressed as a linear combination. Let E mu E be the basis. Now instead of writing I, the this ijk, I will use mu. Okay, it is usual practice to denote the indices by mu. Okay, so any vector in this Minkowski space can be written as a linear combination of this basis, summation or mu, but I will not write summation. Okay, it's Einstein, it's called this, when the indices are repeated they are summed over, it's called Einstein summation convention. Okay, so mu runs from 0, 1, 2, 3. Okay, fine. Okay, this Minkowski space come up with the inner product. So this is defined as, you consider two such vectors V and W. Inner product of V and W is defined to be V0 W0 minus V1 W1 plus V2, there is a bracket, so it will be V2 W2 plus V3 W3. As far as this is concerned, this is just your usual inner product in R3. So this will be V0 W0 minus V dot W. Okay, so this is your usual dot product. Usual inner product in R3. Okay, once you have the metric, once you have the inner product, you have the metric on this space, Minkowski space. So eta VW is defined to be this. Okay, fine. It's the inner product. Okay, so you choose action of eta on orthonormal basis in Minkowski space. E mu will be inner product E mu with E nu. Inner product E mu with E nu. Okay, what is this inner product? This inner product is defined to be, so now I need to define this basis. Okay, how I should define this basis? How we define the standard basis in R3? E1 as 100, then E2 as 010, and so on, right? So one of the bases, so say E0, so mu runs from 0, 1, 2, 3, right? E0 will be denoted by 1, 0, 0, 0. Okay, then E1. Okay, E1 will be what? E1 will be 0, 1, 0, 0. This is a one basis. Then E2 will be 0, 0, 1, 0, and E3 will be 0, 0, 0, 1. Okay, fine. Now E1 inner product with E1. Okay, how you define this? Okay, this is E1 0, E1 0. Remember, this is vector. This denotes its zeroth component. Okay, you understand? Minus E1 1 E1 1 plus E1 its second component is not square, it's second component. E1 3 E1 3. Okay, so E1 was what? E1 was this 0 1 0 0. Okay, let us see whether this is correct or not. Okay, so E1 0, what is the zeroth component? Okay, zeroth component is 0, right? Okay, so E1 0, this will be 0, so this is 0. Okay, minus E1 1. Okay, so E1 1, what is the first component? This is zeroth component, first component, second component, and third component. Okay, 1 and so 1 1, so it will be 1. Okay, so this is 1, so this is 1 plus E12 E12. What is E12? E12, that is 0, so rest of the entries will be 0. Okay, so this is equal to minus 1. Okay, so E11 is minus 1. E00, you can show that this is equal to 1. Okay, E22 will also be minus 1 because of this minus sign, will be minus 1, and E33 will be minus 1. Okay, and similarly you can show that E0 with 1 2 3 is 0. Okay, so you will have E0 with EI, I not equal to 0 is equal to 0, and EI with EZ. What will be EI with EZ? Hmm? It will be -1 when I is equal to J, okay, and it will be 0 if I is not equal to J. Okay, now tell me, what should I do? Should I change my this definition or not? If you understand whatever I discussed so far, you will answer this question. Is the question clear? See how I define this. Okay, I define this in analogous way by making the analogy with Euclidean space. In Euclidean space, say in R3, how we define standard basis 1 0 0, 0 1 0, and 0 0 1. So I also define in this way. Is it correct? Is it the correct way to define? Hmm? Or should I change something? See, this will tell you this part. Hmm? What should I do? See, this should act as your usual three vectors, right? What is your see? I and J are not zeros. Okay, they are different than zero. So they are this IJ takes value 1, 2, 3. Okay, okay. So your EI, okay, will be always of this form. Zero will all the first entry will be always zero, and rest will be what? Rest will be there will be zeros except ith position here. Okay, so if it is 1, then there will be 1 here, 0 0. This is the way we define, right? Okay, and by with this definition I am getting this. But suppose if I write explicitly, so this is E1, E2 will be 0 0 1 0, and E3 will be 0 0 0 1. Okay, so what is common in this? In all these three, this will be 0. So this the first entry is always 0. Okay, the rest of these, they are exactly in the same way as your basis vector in R3. So if I take their dot product, I should get a dot product in R3. So what should I do? To take this as an exercise, you just see whether this definition is compatible with your usual definition in R3 or not by choosing this as my basis vector in Minkowski space. Okay, I will leave it to you as exercise. Okay, if not, then you change something here. Okay, and what change you need to do, that you figure out. Okay, so in Minkowski space we define the inner product in this way. So eta acting on e mu is inner product of e mu with e nu, and this is eta mu component of tensor eta. Okay, I will tell you the answer. This should be 1 minus 1 minus 1 minus 1. Now you figure out what changes you need to do. As a matrix, this will be eta mu matrix. In a matrix form, it will look like this. Now you figure out what I need to do here. Okay, clear? You see this. Just replace insert, instead of V, insert E0. Instead of W, you insert E0. Then E1, E1, E2, E2, E3, E3, and then E1, E2. You use this definition. Correct. You will get what changes you require to do. Clear? Fine. So this is the metric on your Minkowski space. So once you have the metric, okay, we can think now of raising and lowering these indices. So any given vector, for any given vector v mu, okay, I can talk about the component of corresponding dual vector v mu. This will be equal to eta mu nu v nu, same as your earlier definition. Okay, fine. Okay, I'm changing nothing. Okay, our procedure, the procedure which I illustrated here is general. I never assumed any specific vector space. So instead of using ij, I'm using mu nu as some Greek indices. Okay, fine. Okay. Given a dual vector v mu, or instead of now talking about vector and dual vector, I will talk contravariant vector and covariant vectors. Okay. So given a covariant component of vector, I can obtain corresponding contravariant component by raising the indices. Okay, this is lowering the indices, and this is raising. Okay, you can generalize this to any tensor. T, any contravariant tensor can be converted to covariant tensor. Okay. Eta mu alpha, eta nu beta, T alpha beta. Okay, fine. Is it clear? Similarly, any covariant tensor of rank 2 can be converted to contravariant tensor by using this metric eta mu alpha, eta nu beta, T alpha beta. Okay, so that's it. So this is the very brief introduction to tensors. Okay, and now from now onwards we will apply this to special relativity. Only one point remains. Till now we were using general basis EI. Okay, and I never assumed anything special about this basis. Sometime I assumed that this basis is orthonormal. That's it. Okay, but from now on we will use what is known as coordinate basis. And in the next lecture I will tell you what do we mean by coordinate basis? This is the only point which is remaining. Okay. From now on, we'll use the coordinate basis. Okay, this is specific type of specific basis. Okay, where in brief, the coordinate basis for V, for vector space V, is just is the basis given by your partial derivatives. Okay, these are nothing but del xi. Okay, and corresponding dual basis will be bxi, your differentials. Okay, that's it. So this is the point which I would like to illustrate, okay, in next class. Okay, so in this basis you will have, you will work in this basis from now on, but there is no reason to work with this basis. Okay, but we will use, there is no harm also in using this basis. Okay, the advantage is clear, because when we talk about, ultimately we'll talk about vector fields, that is at every point in Minkowski space or at every point in Euclidean space we will attach a vector, and that will constitute a vector field that will change from point to point. So it is better if we use the coordinate basis. Okay, fine. Okay. In which each point is labeled by four coordinates. That coordinate basis we use. Okay, so I'll stop here. Day after, next class will be on, today's Monday, so next class I will take on Wednesday, same time. So is there any other thing on Wednesday afternoon?
No, sir.
Sure, right? Wednesday afternoon there is no lab, no tutorial. Pardon?
Actually, there is editing for you.
So can you, I can't hear you basically. So can please raise your voice. Hello?
There is ED2 tutorial, but if you schedule, then we can tell sir that our lecture is arranged so that.
No.
They
But
can change their time.
see, the point is ED2 tutorial is in schedule, right? In the timetable, or in the timetable, is it there or not?
Yes, sir.
No, sir, not on Wednesday.
Not on Wednesday, so I can take that. Okay, if it is not in the timetable, then I can take, if there is nothing in the timetable. Okay, and if it is not previously arranged, then I will take the class on 2:15 on Wednesday. So just confirm my statement. So can I take on Wednesday now?
Yes, sir.
So I will take on Wednesday 2:15. Okay, so if there is any other change from your part, just inform me. Okay.
Okay, sir.
Hello.
Hello, sir. Yes, I had one question. Sir, in the previous page, where you gave us this exercise, find out this E0, E1, E2, E3. Yes, sir. If I am, what I understood is that your question was that if we treat this inner product as, means vector inner product in R3 space, what should be this basis E0, E1, E2, E3, right?
No, not in R3 space. See, in the Minkowski space, the inner product is defined. Inner product is E mu, inner product with E nu is eta mu nu. If you calculate the matrix, suppose you take E0, mu is 0, what does it mean? This matrix, what is the meaning of this matrix? Meaning of this matrix is that if I take E0 inner product with E1, I must get 0. Okay? Yeah, that is this entry. That is this entry. Okay. Similarly, if I get, suppose now if I take E1 inner product with E2, Okay, I must get 0.
Yes.
Okay, suppose if I take E1 inner product with E1, what entry? I must get -1.
Yes.
Okay, so now is this whatever we are defining here, is it consistent with this? That is what you have to check. Your it may be, it may not change, or it may change. Okay, that is what. Is it clear? I
Yes.
have
Yes.
given you this matrix, so just check whether this basis which I have written down here is consistent with this. Okay, so
Okay.
that means if I take this basis and if I use this inner product, I will get this as a matrix.
Okay.
Clear? Clear?
Yes, sir.
Okay. Suppose,
Yes.
okay, so let us, it's not, there is nothing big, no big deal here. Suppose if I
Yes,
take
it
this,
is.
suppose if I take my E1 is this 0 -1 0 0, and E2 if I take as 0 0 -1 0, what I am going to get? Okay, if you use your this definition, okay, what I'm going to get? E1 inner product with E1. Okay, so E1 0 E1 0, that will be 0, minus E1 1 E1 1, E1 1 E1 1 is -1 -1. Okay, that is 1, plus E1 2 E1 2, that is 0, plus E1 3 E1 3, that is 0. You understand what I am writing here? E1 1, what does it
Yes.
mean? It means that it is the when I write E1 0, it is the zeroth component of this vector. Hmm?
Mhm.
Okay,
Yes.
this itself as a vector. Now, I can write this as, right, 0 E0 0 E0 plus 1 E1 plus 0 E2 plus 0 E3 as a linear combination of E0 E1 E2 E3, this vector E1. Okay, so this is the component of this vector. Okay, that is E0 1 E1 0. Okay, this is the component of this vector. Okay, that is E11. Okay, E11, that is 1. Okay, and so on. Okay, here now you take the inner product. Okay, you will get this equal to -1. So if I use this, if I define basis like this, I will get -1 E1 with E1. If I use previous way, this one, still I am getting -1. Now which one to use? Both are consistent with this, correct? Now which one to use? That is the question. That is what I am saying you have to solve. Okay, if I use this, then also I am getting E1 inner product with E1 is -1, and if I use this one, then also I am getting -1. Agree? Now question is which one to
Yes.
use?
Yes, sir. Mm.
That you figure out.
Okay.
Okay.
Uh, Sir, can you give any reference of any book for this formulation of tensor that we are doing using transformation?
Tensor, this it's there is no as such, there is no ref, but anyway, so you I'm bit so you which reference you use? So let us see the reference which I forgot the initial, but it is Lichenrovic. Lichenrovic. Okay, Lichenrovic tensor analysis. No, it's not tensor. It is linear algebra. It is vectors and tensor or linear algebra, something. Vectors and tensor, linear algebra, something. I forgot the name. Okay, just search linear. If you
Okay, sir.
if you don't get, I will tell you. Okay,
Okay,
exact.
sir. Okay.
Okay, Lichenrovic, and there is
Okay, sir.
another book called uh, Just a minute. I will see. The way I defined here. No, not this one. Just a minute. Then another, there is a reference which is based on this. Is author is Nadir G1G. Okay, this is tensors and group theory. Okay, this reference is based on this. So this is the parent reference, and this reference is based on this. Okay. Okay, but I would suggest you don't indulge too much into this. I did this just because I don't want any confusion about this about the tensors. That there is always there is a confusion whether the tensor is defined only when the coordinate transformations are defined or not. Okay, the answer is no. That's why I wanted to do in this way. Otherwise, I could have done it in your textbook fashion, your usual Jackson's way. Okay, the way Jackson do. Okay. Okay, but don't indulge too much into the mathematical formulation of tensor. Just try to understand the essential points. Okay.
Okay, sir.
So I will stop here.
Sir, can you explain the contraction of tensor point in short?
Huh? Maybe in the next lecture you just remind me. Okay, I will repeat again.
Okay, sir. Okay.
Okay, because then
Yes,
now
sir.
again I have to. In short, it's not. In next lecture I will do that. Okay.
Yes, sir.
Okay.